All right. Hello, everyone. Thanks for coming. My name is Rick. I'm currently an ML engineer at BentoML. So I'm very excited to share with you an experiment, an LLM inference benchmark we did recently that benchmarks 5 LLM inference backends, which is one of the most important building blocks of AI serving systems. So a quick intro of myself. My name is Rick. And I currently work at BentoML. I'm mostly working on the cloud deployment optimizations. I'm also a member of Catalyst Lab at CMU. I'm currently working on a MLC-LLM project. So my research interest is to use machine learning compilations to optimize the LLM serving. So to give you a little bit background of why LLM deployments are challenging. So I want to break this down into 5 aspects. So first of all, LLM models are large, easily like multiple billion parameters. So it is very challenging to efficiently serve LLMs under different user loads. So we need to do careful concurrency management and also resource allocations. And secondly, latency and throughput is very hard to get optimized under these large models. So we need to sometimes be careful about like the low response times, for example, TTFT, which is the time to first token. And also we want to measure our token generation speed, measured in token per second. And also for LLM deployments, we want to focus on the compatibility. We want to support as many models as possible, and also provide support for different quantization schemes. For example, AWQ, GPTQ, 4-bit, 8-bit quantizations, and hardware devices. Also, we want to make sure the LLM deployment system we choose has good usability. We want to simplify LLM updates, model deployments, and system integrations. And finally, security and reliability is also very important. We want to make sure our data is securely stored, and we have secure and reliable access to our models. So all of these our LLM inference backends can address these problems. So we want to make sure, for example, I think LLM inference backends mostly solve the first 4 problems: scalability, latency, compatibility, and maintenance, and maybe not so much on the security reliability side. So it is very important to choose LLM inference backends that suits most of the needs from the user. So why choosing the right LLM inference backend matters? So I want to break this down to 3 aspects. First is performance. So we usually measure performance of an inference backends from 2 metrics. One is TTFT, time to first token. Basically, how much time you have to wait until the inference backend return the first token. So sometimes we call it latency. And the second is sometimes we refer to it as a throughput, which is the token generation rate. So basically, what's the token per second the LLM inference backend return to the user. So we want to make sure we choose a backend with low TTFT and high token generation rates, and under like the various user loads. So we want to make sure the backend scale to high concurrency use cases. The second aspect is capability. So basically, we want to make sure the inference backend supports the model we want to use. And also, we want to make sure the hardware we actually run the model on is supported by the backend. And finally, I think this one is also very, very important. We want to make sure the dev experience of that is good. We'll make sure it's easy to set up the environment for the inference backend. And also, the backend has a good documentation and quality examples to integrate into the current system. So to give a little bit context on why BentoML is trying to conduct this benchmark. So BentoML helps user to build and deploy AI systems, or more importantly, compound AI systems. So it tried to unify these 3 components: model inference, compute infrastructure, and application code. So it helps the AI teams to ship and build AI systems faster. And BentoCloud is a platform that also helps users to build fast LLM serving APIs or servers. And actually, the inference backend is a very important part of this entire ecosystem because it is very important to ensure the performance, capability, and dev experience of AI systems. So we conduct a research on 5 different LLM inference backends: vLLM, TensorRT-LLM from NVIDIA, LMDeploy, TGI from Hugging Face, and MLC-LLM from developing at CMU. The first benchmark we did is about the performance. So basically, we built an API server using the BentoML framework. And inside the API server, we pick the inference engine we selected from the 5 inference backends we selected. And we also built a benchmark client that basically sends requests to the API server and get the response from the API server. And then the API server is deployed to BentoCloud. And then we measure and collect the metrics from these request and response layer and run the benchmark scripts and then collect the results. So here are some details of our benchmark. So we run the benchmark on 2 models. One is Llama 3 8 billion models, which is in FP16 precision. The other is Llama 3 70 billion models running on 4-bit AWQ quantization. So this is to measure how inference backend performs on quantized models. And then we randomly select prompts from the Databricks Dolly 15K dataset. And we run the inference backend on the A100 80 gig GPU. And because these LLM inference backends are open source and evolve very quickly, so they may have more up-to-date versions today. So please know, like, these are the library versions we use for the benchmark. Oh, sorry. Yep. And then for the actual deployment, as I mentioned earlier, all the models and the LLM inference backends are deployed to BentoCloud with the default engine configurations. We only enable continuous batching, flash attention, and prefix caching, and then set tensor parallel size to 1 because we only need 1 GPU for that. We did not really tune the inference configurations. So we didn't tune like GPU memory utilization, max number of sequence, page KV cache, block size, etc., because we think this is an implicit measurement of the usability of the framework. And then for the benchmark client, we spawn up to the target number of users within 20 seconds. And we make sure the client is sending concurrent requests with randomly selected prompts from the Databricks dataset. And then we test this benchmark client with 10, 50, and 100 concurrent users. So you can refer to this link for our source code for the benchmark client. And then this is the result. So we start with the Llama 3 8 billion. This is the time to first token. So the lower, the better. We can tell like mostly LMDeploy, MLC, Trt-LLM, and vLLM has a pretty similar TTFT, under pretty good TTFT under all user loads, whereas TGI kind of has a pretty high TTFT, especially for lower concurrency use cases. And looking at the token throughput, we can see like probably like LMDeploy and TRT are the top tier, especially under high user loads. And MLC, TGI, and vLLM are kind of similar under high user loads, and probably MLC is doing a little bit better on the lower user loads. And now looking at the quantized 70 billion model, it's kind of similar, whereas LMDeploy, MLC-LLM, TRT, and vLLM is doing pretty good in TTFT. only MLC is probably a little bit high on the high load size, high load case. However, TGI, again, it's not doing so good on TTFT. And for the throughput on the quantized model case, we can see it's a pretty clear. There are like kind of sort of two tiers. So one is LMDeploy and TRT is doing pretty good under all cases, whereas the remaining 3 backends are doing less optimal in all 3 cases. So, sorry, let me go back here. So beyond performance, we also measure some other, for example, capabilities-wise, we have measured quantization and then the number of models supported and hardware limitations. So for LMDeploy, everything is pretty well supported, but only thing is that it only optimized for NVIDIA CUDA, whereas TensorRT also only supports NVIDIA CUDA, but its quantization support is less supported because it's supported via this model OPT project, and it's not implemented for all the models. vLLM, it has a pretty good support for quantization, but it's through Auto AWQ. Or you can also download like pre-quantized models from Hugging Face. However, the performance-wise, as we can see in the previous benchmark results, for vLLM, quantized models are not that well optimized. However, for vLLM, the hardware limitations are not there. Like it supports a wide range of hardware backends. MLC-LLM quantization, pretty good. Hardware, because it uses a machine learning compilation approach, so it supports a wide range of hardwares. TGI, also good quantization support, and then good hardware range. And finally, let's look at the dev experience. So MLC is the only backend here that does not have a stable release. It's still ongoing. So let's probably wait for its official release, and we can see maybe it will solve more problems we mentioned here. And also, it is important to notice that some of the backends here require model compilation. This means that it requires an extra step before we can actually serve the model. So namely, TensorRT-LLM and MLC-LLM require this model compilation step. So it potentially introduces some extra overhead before we can deploy the model to the cloud. And also the learning curve is important here. So this is from my own experience. So to learn and how to deploy or build a model in LMDeploy, vLLM, and TGI, it's very fast, requires maybe less than 2 hours. For MLC-LLM, because it requires this extra model compilation step, it's probably like around 5 or 6 hours. But for TensorRT-LLM, the learning curve is pretty high, that you have to learn these different components like the Triton backend and then the Triton server. So for me, it's probably more than 6 hours. And also, it's more important to know the open source community. So the most popular one here is definitely vLLM, with a lot of open source users and contributors. And TGI, MLC-LLM, TensorRT-LLM, these are similar on a similar level, I think. And then finally, LMDeploy, which doesn't really get a lot of attention, but I think it's a great potential here. So general, I want to make some recommendations regarding all the 5 backends. So LMDeploy, definitely performance-wise, it's really good. Low TTFT and highest decoding speed. It's also very easy to use. However, there are some limited model support in its TurboMind engine. So the TurboMind engine is the one they optimize for CUDA kernels. So maybe if you want to use, for example, Mixtral, Gamma 2, or V3 model, you probably cannot find it in its TurboMind engine. TensorRT-LLM, similar performance compared to LMDeploy. However, it has a pretty high learning curve, as I mentioned, and there are some integration challenges due to its dependency on the Triton inference server. And also it has to perform this extra step of model compilation and checkpoint conversion. vLLM, performance-wise, it has to catch up with LMDeploy and TensorRT. Also, it's not very optimized for AWQ quantization. However, it's pretty very easy to use. It has a strong open source community, very extensive model support, and broad hardware compatibility. So yeah, and MLC-LLM, it's pretty innovative. It uses this traditional compiler approach to deal with model inference problem. It has a pretty great performance at low or concurrent users. It kind of right now kind of struggles with top tier decoding speed at higher concurrency. But let's see if it can solve this problem when it has an official release. And finally, TGI. Its TTFT performance is pretty poor, and I don't really see it has any advantage in token throughput as well. And finally, I want to mention a little bit about tuning for backends. So I use TensorRT as an example. Because I mentioned earlier that I did not really tune for the engine configurations for the benchmark because this is an implicit measurement of usability. But I do want to note that there is room for improvement if we actually tune the backends. So there are, for example, for TensorRT, there are some tunable parameters like max batch size, max number of tokens, multiple profiles. This is actually whether you want to enable like multiple optimization profiles, so it can potentially choose a better CUDA kernel, and chunked context, so you can chunk the prefill into multiple chunks, and you can also tune like the post-processing instance count to specify how many process are there to do the actual de-tokenization. So after the tuning, we can see there are a lot of improvements in TTFT, especially under high concurrent use cases. And there are some slight improvement of token generation rate or the throughput after tuning. So I think the takeaway is that to choose the right LLM backends, it is not only important to understand your own use cases, but also you want to make sure you know the in and outs of the specific backend of your choice, so then you can make sure after tuning your specific backend, it can achieve its full potential. Yep, so this is all I'm presenting here. Please feel free to ask any questions.